Okay, so we've got all our pieces together now for our frequency response analysis. Uh, we've got an idea of what frequency response is. We're subjecting the system to a sweeping sine wave, seeing what the response is both in magnitude and phase. And we've learned to plot it with a Bode plot. We have learned about our tools, our gains, poles, and zeros, and how we can reshape the Bode, or how the Bode is shaped by those poles, zeros, and gains. And so now we've got all the pieces. Now we need to put the puzzle together. Ultimately, what we want to do is design a controller that will give us the response that we're looking for from our system. And so, as I've mentioned before, we're going to be using a technique called loop shaping to do this. And this is where we're going to take our tools and we're going to reshape the Bode, the open loop Bode, in order to get the proper response from the closed loop Bode and from our time domain response from our system. And you're going to have to put your thinking hat on for this. This gets takes a little beyond what we've been going to, but it's very doable. So let's think about this a little bit and see what we're up against on here. It's actually pretty simple. We're going to divide the the system into a couple different zones, and we're going to try to control the magnitude plot in those different zones, which will then control the response of the system. Now, if you think about this, in this plot that graphics that I've got shown here, we have a couple things going on here. We have the closed loop Bode there in the blue, and the open loop Bode, or the magnitude plot of the Bode, in the red. And then we've got a new plot in there called the error transfer function, and it's plotted in the green. So let's step back and think a little bit about what it is we want the closed loop Bode to do. Let me switch here for just a second. What we want the closed loop Bode to do. Okay, we've got our magnitude ratio, and we've got our phase. And what we would like the magnitude ratio to do is be at 1, or in the dB scale, we would like to have it at 0. We would like to have it at 0 the whole way. That would 0 dB is a magnitude ratio of 1, and so what we put in is what we get out. I mean, that would be the ideal situation. And as far as phase, we would like our phase to be at 0. We don't want any phase shift in there. So we would like to have 0 on both of these. That would be the ideal closed loop Bode for a system. That would be perfect. That would mean whatever we put in is what we get out. And that's our desire from our system. Now, the reality is that we always have parts of the system that will go into resonance, that will start messing with our signal and distorting our signal, and we won't end up with what we put in. A typical second order system would have a Bode that would look something like this. Okay, you would get a peak in here. We saw that when we were plotting our Bode. Second order systems had created a resonance in there, and as a result, our phase would go like this. And so in this case, what we have, and this is real case, okay, we have a situation where we have stuff here that we cannot control. It's doing exactly opposite of what we want it to do. Okay, it's not behaving well at all. Okay, so what we do in these cases is we say we don't want any portion of our signal to get in there and excite any part of the system that could cause resonance and cause us to be something different. And so we will come in and design a controller that will come in here and reshape our body, at least the back end of our body, to attenuate this very rapidly, to take it smaller, to attenuate it. And so in doing that, what we do is any signal that gets in there that might excite it, the outcome is nil or zero. Okay, so we want to attenuate it on the back end of this. And here where we can control it, in this zone, what we want to do is we want to make that signal as strong as we can. Now, we can't see this on the closed loop body, but on the open loop body, we'll be able to see how we make that happen. But we want to make our relationship, our magnitude ratio here in our open loop to be as large as we can make it, and that will give us what we call good tracking in our closed loop body. And so it will tend to stay right on the signal and as well as it can, because we're putting tracking. And then our third region in here that we have in here is our crossover region, our bandwidth, and in this case, we're going to be mindful of our phase margin, and we're going to try to maintain a good phase margin in here. Now, I know we can't have phase margin on a closed loop, but I just put it in there for visualization purposes. Okay, so we've got three bands. We've got our low frequency, which we're going to try to drive up in our magnitude ratio in our low frequency. We've got our high frequency, which we're going to try to attenuate the magnitude ratio. And then we've got our intermediate zone, our crossover zone, where we're going to try to maintain a specific slope in there so that we get a acceptable phase margin. Okay, so that's where we're going with this. Let me get back to my graphics again here. Loop shaping, there it is. Okay. Now, so here's what we've got. We've got our closed loop in here, and so we've got our closed loop. And like I said, we're going to try to maintain a magnitude ratio of 0 dB for as long as we can, and then where it's not behaving well, we're going to attenuate it off and drop it down as quickly as we can. Okay, now think about this. How can we do that? Well, we have poles and zeros in our controller that we can use to reshape our open loop in order to control our closed loop. Now, if we look at this, what we can see is that, and we have to go over here to some equations in here. We take our standard closed loop system, and we write just the open loop in here, and of course that's x over e, and it's the open loop transfer function. Well, we can also write the closed loop transfer function. We've been doing this all semester. It's no big surprise. That would be the closed loop transfer function, which is x over xc, x sub c. Then we're going to create a new transfer function called the error transfer function, or sometimes the sensitivity transfer function, that is the error over x sub c. And that's the error transfer function, and it's represented this way, 1 over 1 plus gs. All right, so nothing too surprising there. It's just a little bit of algebra and manipulation in there for that. Now, what I want you to think about is when our open loop transfer function, the magnitude of our open loop transfer function becomes large. Okay, when our open loop transfer function becomes large, what happens to our closed loop transfer function, and what happens to our error transfer function? Well, if we look at our open loop or our closed loop, we have a large G and a large G. We've got a little 1 there that's insignificant, but basically this transfer function goes to 1 as G sub or our open loop transfer function is large. And if we look here at our error, if our G of S goes large, then we end up with 1 over large, and that ends up with a small value. Okay, so it's inversely proportional to the size of our open loop transfer function. Okay, so then we look at it the other way. What happens if our G of S goes small? Okay, then our transfer function, if G of S goes small, then our open loop or closed loop transfer function is essentially equal to our closed loop transfer function. And so we use that in here to create this graph. And we have over here where our closed loop transfer or open loop transfer function is small, then our closed loop and our open loop are going to be together. Okay, where our G of S is large. Okay, the magnitude here of our open loop is large. Okay, it's large here. Then our closed loop transfer function is going to be 1 or 0 dB, and our error is going to be small. Okay, so we put all these pieces together, and what we end up with is this graph in here like this. Okay, now what we're going to do is we're going to desire to push our open loop transfer function up as high as we can in the low frequencies. Okay, this gives us better tracking. We're going to try to push it down here to attenuate it, and then we're going to have this 20 dB per decade slope across the crossover. Now, why do we do that? Because of our phase margin, right? Our phase margin. Because our phase margin, we want it to be a good, solid, positive number. And at 20 dB per decade, we would have a 90-degree phase margin in there, which would be nice and stable for our system. So that's the objective of the loop shaping method. And we have our tools. We have zeros that will push these slopes up. We have poles that will push them down. We have our gain that we can move it up and down with, move our magnitude plot up and down with. So we're just going to massage this open loop transfer function with our tools to get it into this shape. Okay, so that's where we're going. That's what we want to do with it in a nutshell. And this speaks basically of what I've talked about the crossover. Here we are going to assume in this that the crossover is equal to the bandwidth. For a well-designed system, for a well-behaved system, that's true. And we want the 20 dB per slope for crossover for stability. And then we want the high gain at low frequencies for good tracking. And we want to decrease in magnitude after the crossover to a low sensitivity or to minimize the noise in the system. Okay. All right. So now the problem with this huge problem is this. Okay. Is that point in there. If we had that point in there, then we could figure out where the crossover is. We could use our poles as zeros to reshape it to a 20 dB across that crossover and then attenuate it on down afterwards. We could use our gain to slide it up there and reshape it with our poles and zeros. Okay, but where is this crossover? Okay, where is that guy? And this gets back to something we talked about earlier in the semester. There's two ways of determining this. One is high frequency. Okay, if you have a known high frequency out here, okay, we've got some stuff happening out there that's high frequency that we don't want to get involved with, then we can step back 1 decade from that and call that our crossover frequency, and design around that crossover frequency. So, which is a legitimate way if you know that where the high frequency is. That's a good way to establish that crossover. Once you have the crossover point, then everything else just flows. Okay. The other way, if you don't know the high frequency, we design based on specs, time domain specs. Remember, we talked about this early on. What happens if we need a settling time of a certain value? What happens if we need to minimize the peak overshoot? With those, we can determine an omega, right? We can determine an omega n, and we can determine then a zeta, omega n, and with zeta and omega n, we can establish a crossover. Actually, all we need is the omega n. We can establish a crossover that meets our spec, okay, and hopefully it keeps us out of any high frequency. In that case, we may leave some performance on the table, but if we're adequate for our application, then we call it a day and are good, because if we start pushing it, we might push into some high frequency that we didn't anticipate and cause ourselves more problems. Okay, so that's basically in where we're going with this, and what we're going to do with it. So we'll go through a couple of examples and see if we can't flesh this out and make it so that we can actually do it.